So, hello dear students. Now in this subunit, we are going to discuss sources of electrons. The fast electrons that come out in the form of beta rays are basically a nucleus which is emitting a beta particle along with gamma rays and other particles as well. So, a neutron converts into a proton inside the nucleus and a beta particle is emitted because of charge conservation. So there are different sources of fast electrons. First is basically a radioactive nuclei which is undergoing beta decay, or some electrons ejected out through a process called as internal conversion, or electrons that are coming out of the atom in form of OJ electrons. Now what is beta decay? So the most common source of fast electrons in radiation is beta decay, and basically it's some kind of radioisotopes which is exhibiting radioactivity and it decays by beta minus emission. So the process is written schematically like this. A nucleus species X, which has got A as mass number and Z as charge number, converts into a nucleus species Y with mass number remaining the same and Z number increasing by 1, along with a beta minus and another particle called an antineutrino. Now X and Y are said to be the initial and the final nucleus species. Antineutrino is represented by this nu bar, and since antineutrinos or neutrinos do not interact appreciably with matter, they are undetected for practical purposes. So the total energy is shared by the antineutrino, beta particle and the recoiling nucleus. So the recoiling nucleus basically has a very small recoil energy and it is much below the ionization threshold, and it cannot be detected because it does not ionize the surrounding medium. So the only significant ionizing radiation turns out to be the beta particle, because both the nucleus, the final nucleus and the antineutrino do not interact appreciably with the surrounding medium. So how are they produced and where are they produced? So basically a lot of nuclear bombardment takes place in a reactor, and the stable material becomes beta active due to neutron bombardment, and large assortment of beta emitters are produced in a reactor flux. So in a nuclear reactor, the material that is producing through neutron bombardment are generally beta active, and they are also in the excited state. So they are not in those nuclei are not in the ground state. So they not only emit a beta particle because they are unstable, but also since they are in the excited state, they also fall to the ground state and in the process produce a gamma ray. So in this figure, you can see a cobalt-60 with 27 protons. When it is bombarded, it converts into nickel, which is 60, and proton number is 28. And this nickel is in the excited state, which is represented by the star. So the star on a nucleus species represents an excited state. So it emits a gamma and also a beta. So a beta particle and a gamma ray are emitted simultaneously, and finally we get a stable Ni60 with 28 protons. Here we show the half-lives of different nuclides which are undergoing beta decays. So a triton, which is hydrogen with 3 nucleons, has a half-life of 12.26 years and an endpoint energy of 0.0186 mega electron volts. Similarly, carbon-14 has a half-life of 5730 years and an endpoint energy of 0.156 mega electron volts. So the endpoint energy is the actual total energy that is released in the decay. And there are other nuclear species, as you can see, which have different half-lives and different endpoint energies. So what is the Q value of a radioactive decay? So a Q value is the total energy that is produced during a nuclear reaction. In case of beta decay, the beta particle energy varies from 0 to beta endpoint energy. That is, the energy that is coming out from the nucleus in the form of beta rays. The energy of the beta rays is not unique but is variable. It starts from 0. Some of the beta particles have almost negligible energy, and some of them have a very high beta endpoint energy. So the endpoint energy is numerically equal to the Q value. But not all the beta particles have that energy. So the energy released by the nucleus goes into something else as well. So here we see a chlorine-36 with a half-life of 3.08 into 10 to the 5 years converts into argon-36 through beta emission, and in the process different beta particles have different energies. So you can see that the relative yield versus the beta particle energy. So some of the beta particles have almost zero energy, and some of the beta particles have energy equal to the endpoint energy, which is 0.714 mega electron volts. And rest of the beta particles have intermediate energies. And you can see the maximum number of particles, which is the maximum yield, is having energy between 0.2 to 0.3 mega electron volts. So why is it so? Why is it that the total energy is not given to the beta particle? It is simply because another particle, which is the antineutrino, is also emitted, and so it shares the total energy with the beta particle. Some of the energy, the total energy that is emitted in the decay process, goes to the beta particle, and some of the energy goes to the neutrino or the antineutrino. And that sharing is not fixed. Sometimes the antineutrino has a higher share of energy, and sometimes the beta particle has a higher share of energy. And so if not all the beta particles are having same energy, some are having low energy, some are having high energy. And this was the first evidence for the existence of another particle, which is an antineutrino, which was discovered later, but it was hypothesized on the basis of this curve or this data that was seen in the decay process of chlorine. Now the second process is the internal conversion. The beta decay process produces a continuum of energy, but to get a unique energy, that is a beta particle or a fast electron with a monoenergetic energy, the process of internal conversion is utilized. The internal conversion produces monoenergetic or unique energy electrons. So discrete and unique energy electrons are produced during the process of internal conversion. In the process of internal conversion, what is happening is that an excited nucleus falls to the ground state and produces a virtual gamma ray, which is absorbed by either the K shell or an L shell or a higher shell electron. So in this figure, a K shell electron absorbs the gamma ray, which is produced by the conversion of an excited nuclei or a nucleus into the ground state. And then when this electron gains energy, it is ejected out from the K shell. And this is this electron that is an internal conversion electron. Sometimes a higher orbital electron jumps to the vacancy created by the ejection of the K shell electron, and in the process produces X-rays. So in the internal conversion, a K shell electron is ejected, and then simultaneously an X-ray can also come out. So the energy or the kinetic energy of the electron that comes out from the internal conversion is just the excitation energy of the nucleus minus the binding energy of the electron. So the shell which is binding the electron, either K shell or L shell or M shell, the binding energy of that shell is subtracted from the excitation energy of the nucleus. That is the energy that the nucleus has in this excited state. So the energy that is released when the excited nucleus falls back to the ground state minus the binding energy is converted into the electron kinetic energy. So here is an example. You have indium-113 in an excited state with an energy of 393 kiloelectron volt and a half-life of 100 minutes. So through internal conversion, it falls to the ground state and two electrons, monoenergetic electron beams are produced. One electron beam is 365 keV and the other electron beam is of 389 keV. So the K shell conversion takes place, which gives rise to 365 keV electron, and an L shell conversion takes place, which gives rise to 389 keV electron. On the y-axis is the relative yield, so the K shell is converted with a higher probability compared to the L shell, which is converted by a lower probability. So we have more K shell electrons compared to the L shell electrons in this case. So here generally we are showing different parent nuclei which have different half-lives, which are converted into different modes like electron conversion or beta emission, and their decay product energy and the conversion electron energy is also shown. So the transition energy of the decay product is 88 in this case, in the first case of cadmium 109. But the conversion electrons are having energy 62 and 86, simply because the transition energy or the excitation energy is subtracted by the binding energy of the electron in the K shell or the L shell. So the total energy of the electron is lesser than the transition energy of the decay product. Now the next comes the Auger electrons. So in this process, the electrons originate from the atom rather than the nucleus. So a previous process in which an electron from the atomic shell is captured by the nucleus creates a vacancy in the shell. So a captured electron, the nucleus captures an electron from one of the shells of the atom, and it is producing a vacancy in the atomic shell. So an electron from a higher shell falls to a lower level and it produces an X-ray. The energy of the X-ray is equal to the difference in the energy of the two orbitals. Alternatively, this energy can be transferred to one of the outer electrons, causing them to eject from the atom. And this electron is called the Auger electron. So you can see here, from a higher shell to a lower shell, electron is jumping because a vacancy is created in the lower shell, and in the process a K alpha X-ray is emitted, which is the energy which is equal to the difference in the energies of the two shells. The energy of the K alpha electron is actually absorbed by one of the Auger electrons, and so the total energy of the K alpha X-ray is converted into the binding energy of the Auger electron plus the kinetic energy of the Auger electron plus some residual energy which is produced when the energy is absorbed. Some of the energy is converted into a photon of a lower frequency. So a frequency, it's a scattering process in which an electron is scattered and a K alpha X-ray is scattered also, and a photon of lower energy is produced along with an Auger electron of energy E. The Auger electrons basically give discrete energy spectrum. The energy of the Auger electron is relatively low compared to beta particles or conversion electrons because the energy is coming from the shells of the atom. So the electrons in the atoms have lower energy compared to the energy of the nucleus, which is of the order of MeV. The electronic energy of the atomic shells is of the order of kiloelectron volts, and the energies, typical energies in nuclear conversions are of the order of MeV. So basically an OJ electron is of the order of kilo electron volt. That is the kind of energy that one gets when you produce an OJ electron, or an OJ electron is emitted in the process. And basically this, since the energy is low, this OJ electron can be absorbed by the sample itself or by the detector window. So the whatever detector you are using to measure the radiation, it might be so that the window of the detector might absorb the low energy OJ electron.